Machine learning doesn't exist yet. We only have a pile of examples and the desire to predict one number from another. Today, we invent the simplest possible prediction machine, a line. Not because lines are fancy, but because they are the first object you can fully understand, debug, and improve without any magic. We start with a data set, pairs of numbers. Think of X as something you can measure and Y as something you want to predict. The first question is not what algorithm, but what are we even allowed to do with X? If we want a rule that's stable and understandable, the simplest rule is multiply X, then add a constant shift. So we propose a machine with two knobs. One knob controls tilt, the other controls vertical shift. For any chosen knobs, the machine outputs a predicted Y for each X. This is not learning yet. This is us choosing a family of rules that's small enough to search and expressive enough to capture a trend. Let's pick a specific line, say tilt equals 1, shift equals 1. For each data point, the model makes a prediction. The difference between prediction and reality is the error. Visually, each error is a vertical gap from the point to the line. If our line is good, these gaps should be small and not systematically positive or negative. Now we hit the core problem. Which line is best? If you and I choose different lines, we need a single number that declares a winner. That number must summarize all residuals. If we just add residuals, positives cancel negatives, and a terrible line can look perfect. So we need a score that can't be cheated by cancellation. Before we commit to any scoring rule, notice what the line is actually doing. It's projecting the messy cloud of points down to a 1- dimensional summary, a direction, and an offset. Each X value gets mapped to a point on the line, then lifted back up as a predicted Y. A linear model is a rigid geometric object trying to approximate a messy relationship. Let's do one concrete numerical pass. Suppose tilt is 1 and shift is 1. For X equals 4, the prediction is 5. The actual Y might be about 4.9, so the residual is 0.1. For X equals 5, prediction is 6. Actual might be 6.1. Residual is -0.1. You can already see cancellation if we just sum them. But even before defining the perfect score, we can explore the space of all lines. Imagine a plane whose horizontal axis is tilt and vertical axis is shift. Each point on that plane is a different line in the original graph. Learning will eventually mean moving around this parameter plane toward better and better scores. So what have we actually built? Not a learning algorithm. We built a hypothesis. The world might be approximated by a rule with two numbers. That's a bold compression. If it works, it's because the data has a roughly linear trend. If it fails in a very specific, visible way, systematic curvature in the residuals that no tilt and shift can erase. This sets up the next unavoidable invention. We need a principled way to score every line, so best is not an argument, it's a calculation. And once we have a score, we need a way to find the best tilt and shift without guessing. Next episode, loss functions, the exact math object that turns fit the data into a single surface we can navigate.